Hey, good morning. This is sometimes I feel like in the United States, the holidays are right now has more than its meaning. It's more about like commercial, right? Or about business. I would say like in the beginning of by the end of the October, we will see a lot of stuff about pumpkins, a lot of stuff about Halloween, a lot of customs, and then people talk about Thanksgiving. People talk about you should send gifts, and there are lots of stuff. And then after Thanksgiving, everything is now in Christmas, and if it's not because of COVID-19, I believe a lot of us were probably already spending a lot of time in shopping around those shopping malls to figure out like what are the gifts that I need to prepare for our friends. And one of the most popular songs that you probably would hear during that period of time is probably Last Christmas, right? So that's why we play that song. But this year, stay safe, stay healthy. I guess some of you might still went shopping last weekend, but if you look at the rocket climbing numbers, you should know that it's probably not a good thing to do like at this point. And you don't want to have the virus as a gift for your friends or your family. So stay safe, and we can still have Christmas in a different way. But before Christmas, we still have 2 lectures to go. We still have one final. So be aware that and a lot of the stuff that we are talking about in these 2 lectures are definitely more important to the rest of your life, because we are going to talk about something that's going to be that's more related to the future. But before we start the lecture today, it's still a good idea to remind you where we are coming from. So last week we talked about modern processors. They are all superscalar processors. But one issue with SuperScalar is that because the instruction level parallelism, meaning that the amount of instructions that can be executed in parallel is not enough, is not sufficient to completely utilize all the functional units within a superscalar processors. So if you look at the pipeline design of modern Intel or AMD processor, they all incorporated the idea called simultaneous multi-threading in a way that we present an illusion of 2 processors or even more processors to the operating systems. And to present such an illusion, all you need to do is to duplicate your program counter. So the operating system would think there are 2 units that accept 2 programs, and 2 sets of architectural register to physical register mapping. Physical registers, you don't necessarily have to double it, but if you duplicate it, that will be better. Instruction queue usually and reorder buffer, because they retire differently, so you should find a way to distinguish 2 sets of reorder buffers for different programs. So that's all you need to do in supporting simultaneous multi-threading. And the early paper is saying that it's less than 6% of the circuits that you need to add it to your die. So it's a pretty good trade-off, considering that you can significantly increase the utilization of your processor. So, by saying that increase the hardware utilization, there's no free lunch there, because you are actually sharing your resource with others. So potentially, instead of getting benefits like the improved throughput of execution, but when we say throughput, it's the throughput of all the programs that you are executed. However, if you just look at a single thread that you are executing on the processor, it may not give you any better, right? So that's the thing, right? So right now, almost every processors incorporate the idea of simultaneous multi-threading to increase the hardware utilization. But there are also other side effects for simultaneous multi-threading. So for example, because when you are dealing with a branch, because in the meantime, instead of executing instructions from a single thread, you can use instructions from other thread to cover the time that you are resolving the branch. So if you have a branch misprediction, the penalty is smaller. Right, so real case like Intel's hyper-threading or AMD's Ryzen processor, they all incorporate the idea of simultaneous multi-threading. So if you look at the modern processor design, it looks like this. So instead of a core supporting simultaneous multi-threading, a single processor right now actually have multiple cores. So and each multiple cores, they have their own private L1 and L2 cache and a shared L3 cache. That's Intel's SkyLake processor. So you can see if we remap the die photo to a more a diagram like this, then the concept of a chip multiprocessor is that a processor chip actually contains multiple processor cores, and as you can see here, each processor core has its own register, has its own L1, L2 cache, and a shared last level cache. And however, if you look at the way how the software treat this multi-core hardware, is that we only assume that we are seeing those cores and those shared cache, but ignoring the fact that in the middle there are also L1 and L2 caches. So there is a misalignment between the abstraction that the software is thinking about of your computer and the hardware that you are really using. So there are quite a few things that we have to deal with when we are operating on this processor. So for example, if we all use the same variables, how can we make sure that all of them would be consistent or coherent? Right. So so it turns out that you have to at least run a coherence protocol and some sort of consistency support. However, there's no free lunch again. So for these pieces of a code, if you are a very careless programmer, write the left-hand side code, and the performance definitely is worse than the right-hand side code. So last lecture, I had an unsuccessful demo on this. So today I'm going to show you the right version of the demo. So the thing that I didn't do well in the last time is because my program I didn't pick the right parameter. So previously I only set the array size to be 16K. However, for this problem to be significant enough to affect your performance, your data must be really big. So here the array size is actually this big, 16K by 16K. To demonstrate that issue, and the number of threads is still 4. So now let's run this program again, and you will see that if I am executing the fine-grained multi-threaded version, you will see that it takes about 2 seconds to execute the whole program. And if you use the chunking version, which that we have a coarser granularity in sharing our data, then it turns out that it's 10 times faster because it only consumes 0.2 seconds in running that program. So so here you can see that, wow, it's really a huge impact if you don't partition your if you don't use the right way to partition your computation. So that's really a huge influence. So now, so that's about coherence. And so we said there are 2 kinds of protocol we run behind on a chip multiprocessor. One is coherence, is regarding what value should be seen when the system is trying to fetch a variable or say a memory address. And consistency is about like all the threads should see the change of data in some order. We haven't talked about consistency so far. We only talk about coherency. So today we are going to continue our discussion on that. And this is the current scoreboard. And as you can see, all the teams are still possible to catch up because we are still having quite a few questions for you today and on Wednesday. So don't give up, even instincts. I mean, you have the chance, even though you might not be able to get a championship, but you might be able to affect others. For example, like, yeah, if you answer more, you can stop those mistakes, right? And then whenever the valors are answering, you just don't interrupt them or something like that. Anyway, all right. So today we are going to continue talking about parallel programming, and we are going to talk about like power and energy, and we will also introduce the concept of dot silicon. So this is the bazaar that I left for you before the end of the last lecture. So the demo in the last lecture, it actually shows that all the four are possible. Right, you can find in the output that all four different values are possible. But why? So here's the thing, right? So this is so you already know that, well, there's and because you have the operating system have different scheduling policy, we may context switch, we may not execute the program in a speed as you would imagine, and because there are cache misses, because there are a lot of branch predictions, a lot of stuff coming up, right? So there's no guarantee that we will execute a program in the order. So if you happen to have your program executed in this, like, okay, when I finish executing my statement a equal to 1, in the meantime, thread 2 just started its execution. However, its execution is a lot faster. Then there may be a chance that before you reach the statement of x equal to b, thread 2 already execute these two statements. So it turns out that that's how you get 1, 1. And for thread 1, there's also a chance that thread 1 is completely running ahead of thread 2, and then you are going to get 0, 1. And similarly, you are also going to see another chance that thread 2 is completely running ahead thread 1, then you are going to see 1, 0. And a lot of you don't believe that you will see a 0, 0, because, however, this is possible. Because if you think about out of order execution and out of order execution, right? We said the idea of out of order execution is as long as there's no data dependency between two instructions, they could be executed in parallel. We could reorder them. So if you look at thread 1 or even thread 2, right? This a equal to 1 and s equal to b, they don't have any data dependency. They don't have any data dependency. And thread 1 is running on its single core. So through this, when we are using this core, we see these two instructions, or say these two statements, has no data dependency. We could reorder them. And when thread 1 is doing its scheduling on one of the core, it has no regards, it has no information about other threads. So we just do our own reordering. So it turns out that x equal to b could potentially be executed ahead of a equal to 1. This is because out of order scheduling. And because every processor has out of order scheduling. So you could potentially see the value of 0, 0 in this way. And again, on the right-hand side, your thread 2 can also do its out of order scheduling. So at y equal to a can run first, and b equal to 1 can run later. So it turns out that you are going to see a 0, 0 in this case. So hope that would help you understand why you are seeing a 0, 0 in this case. So so you are going, so you see this, right? So software programmers, you guys are thinking about, okay, this is how my code being executed. However, remember that the processor has out of order execution. The coherence protocol can only guarantee that we will eventually update that address. And and a compiler can may store values in register and perform memory operations later, right? So and we can reorder your memory operations and instructions. So there's no guarantee, especially in the multi-threaded era. There's no guarantee that both threads they have consistent view of the ordering of instructions. So that's why, in addition to coherence protocols, we have consistency protocols. And but maintaining consistency is really difficult as you read in the textbook. So the most of the processors right now, they only provide relaxed consistencies in a way that you can manually insert and fence instructions to prevent reordering across the fence instruction. So one of the examples that I can show you here is that if you really want to prevent these two instructions or this two instruction gets reordered, you can put m-fence instruction in the middle. So then it will guarantee at least instructions before m-fence won't be reordered to be someone after the m-fence. So that's a very important, if you want to prevent the reordering to mess up your code, then manually insert those m-fence is the key. So if we look at the demo that I just showed you, let me do it now. So so then for the demo that we had in the last time, that's the demo. T-processor. Okay, so I suppose, right, the last time we have an output file, right, and you can see like if we, for this one we have 0, right? So if we want to prevent that to happen, right? One thing that you could do is that, okay, so if you look at the file, this is the original version, and the modified version is right here, right? So I create a macro called update variable A and update variable B, and what the update variable wait, where's the macro? Okay, so the macro update variable do is that it will assign the argument 2 to argument 1 and put an ASM assembly instruction called mfence here. So it's indeed inserting an assembly instruction. So that's why you still need to learn x86 assembly in some sense, right? And now if I am executing this mfence mfence version of the code, let me see, output fence. Oops. Okay. Mfence. Okay, out. Okay, so now, oops. Wait. Is it here? And fence. Oops. Okay. Here we go. Okay. While and fence. TXT. Okay. How come? Already recompiled it. Oh, it's not mfence. Okay, here we go. Hey. Okay. While the true and fence. Oh, shoot. Okay, here we go. You know, sometimes when you just woke up in a cold days, your brain is not completely, function. Oh shit. Okay. And fence. Okay, that's why I need to add this out fence.txt. Okay, here we go. So let's get a few runs and see what are the values you would get. Okay, so I think we got sufficient. So if again, if I can use grep and see if I would get 1, 1 out fence. Oops. Okay, see, I only get, so right now what I get is 0, 1, I have 0, 1. Do I have 1, 0? I have 1, 0. I have quite a few 1, 0. Well, surprisingly, this time I didn't get 1, 1, but usually there is a possibility to get 1, 1. So, because of time, I guess I would probably just trying to convince you that you would supposedly to see 1, 1, but at least, right? So if you have advanced instructions, right, this time at least you won't see like other, oh wait, oops. Okay, so let's look at this. So if we, are we going to see 0, 0? So we don't see 1, 1, and we are also not seeing 0, 0 this time, right? So so with M, so with n-fence instruction, at least I think I should convince you that we are not going to see some values, because A equal to 1 and B equal to 1 must occur or update before the n-fence instruction. So at least you are not going to see some of the odd values, right? But you are still going to see an interleaving between 0, 1 and 1, 0. And sometimes I believe you are also seeing 1, 1. So the takeaways for parallel programming here is that right now, we are in an era that single core is not getting any faster. However, parallel programming is very difficult in a way that, first of all, processor behaviors are non-deterministic because we have out-of-order execution, and you cannot predict which processor is going faster, and you cannot predict when the operating system is going to schedule your thread. And cache coherency only guarantees that everyone would eventually get a coherent view of data, but not when. And the cache consistency is hard to support, like we just see, right? You think I want to see like either always 1, 1 or always 1, 0 or 0, 1. That's not possible, right, from the demo. So parallel programming is really, really hard. Okay, so that completes our part on parallel architecture. And now I'm going to tell you why we end up with this parallel architecture. And the key thing is because we have issues with power and energy. So before we start talking about this topic, I know you have some idea about what is power and energy. So why don't you spend time looking over this question and let us see what your understanding about power and energy. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your current vote, it looks like, well, most of you at least agree with, at least 2 of them are correct. But and some of you think about, a lot of you think about all of them are correct. So it's a good idea that we should go ahead and discuss with your friend. So go. All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the result of the poll, looks like most of you think it's E. There are 11 of you, which I believe that's probably a team, think is D. So instead of having all of you, instead of randomly choosing that one, I want to invite which group you think the answer is D to raise your hand and express your thoughts. Okay, Golden, which team are you?
Instinct, Professor.
Okay, instinct. Okay, and you guys think it's D.
Yes, Professor.
Okay, why? Which one
Uh,
don't you guys agree?
Lowering the power consumption helps extending the battery life. This is what we think
Mm-hmm.
maybe a bit, not fully satisfying the requirement.
Okay, why?
First thing is battery life. What we think is battery life is totally dependent on one thing. It may be different for different processors, and based on the optimizations, it could be changing for different devices.
Say again.
For different devices, based on optimization, it will be different, right?
Mm-hmm.
So that is the reason why we're.
But it didn't still saying why power consumption and the battery life they should be decoupled.
Mm, that is the thought that I have right now.
Okay, but okay, so but glad to hear that. So for okay, so that it sounds like okay. So thanks a lot for your insights um and I think at least instinct you guys discover yes there is something weird here, right? So what is power? What is energy? Right. So that's a very important thing that I think we are missing here. So power is the direct contributor of heat. It means that the amount of work that would generate that we have to do within uh, any moment any moment, right? So if you have to generate a lot of power, if you generated a lot of power, it also means that you did a lot of work at the meantime, right? So if you do a lot of work and it will generate a lot of heat. So if you generate a lot of heat, then your heat dissipation cost would be higher, and your it also increased the complexity of packaging the chip, right? So power is the direct contributor of heat. And regarding energy, is if I run a task for a period of time, right? So for a long period of time, what's the total amount of power that I would consume? Right. So total amount of power, that's energy. So, and the power is just at a moment, right? So so if you want to talk about like, okay, how much battery life or how much money I spend on my electricity bill, that turns out that energy is the most important measurement. So in this way, you should have some kind of feeling that, well, does it always the case that I have lower power, meaning that I have lower energy, right? So before we talk about the answer, announce the answer and show you some evidence, let's keep talking about this concept. So power, there are two types. Well, so first of all, energy is the aggregated amount of power given a period of time when you are performing a task. And there are two types of power. One is dynamic power. So the dynamic power used to be the main contributor of power consumption when you are working on a job. So it's a power consumption because you have to switch the transistor states. And for example, if you are performing ALU operation, it's usually the case that you have to switch the current state from 0 to 1 or 1 to 0. And even for those caches, and like those SRAM caches or DRAM caches, you have to alter your data frequently. So it also causes the switching of transistor status. So and how the power to switch the transistor states is in relation to this equation that contains alpha, the average switches per cycle. C is the capacitance of your transistor, and V square is the voltage, supply voltage of your transistor. F is the frequency, and usually the frequency is a linear function with V. So you can consider this V2 times F as something related to B cubical. And the N, so so the N is number of transistors per chip. So the dynamic power for the whole chip is actually alpha times capacitance times voltage squared times your frequency times the number of transistors in your chip. So that's the power consumption. So as you can see, if we want to lower the power consumption, the easiest way is to adjust the frequency of your processor. So right now I'm giving you a demo regarding this. So previously, when we talk about the when we talk about as a programmer, you can change the frequency of your processor, right? So now we are going to use that again, but we are going to change the frequency of your processor, and then there is a profiling tool called Liquid. We can use it to see how much energy and the power that has been used in our in running a program. So let me do this. So right now, let me go ahead on a processor. Oops. Okay, so now I'm on this processor and this machine, and this machine has an Intel processor. So let me see, where's my demo? 203. Okay, demo. And here I have a script that try to lower the maximum frequency of my processor to be only 800 megahertz. Oh, sorry, not 800. Lower maximum frequency. Oh, sorry, not 800 here. It's 1.2 gigahertz, right? So, and in the meantime, I can also use CPU info to see what's the current frequency. And as you can see now, all the processors are running at 1.2 megahertz, right? And now I am going to execute, wait, I should do it in this way. Okay, processor CPU info, grep megahertz. Okay, now everyone is running at 1.2, right? So in the meantime, I'm going to show you another program that we are familiar with. That was the matrix multiplication, our good friend, right? So, and as I mentioned, we can use the program called Liquid performance control and -G energy, and I can just use the program that I want to profile at the end. And let's see, if we run this program at 1.2 gigahertz, how much time and how much energy it would take. As you could imagine, this would take more time than usual. And if you have the memory, how much time it takes for us to run in the full power version on this processor, it used to be around like 4.5 seconds. And now, because we lower the frequency, the whole program takes about 17 seconds to execute. And from this profiling result, you also see that, wow, this is really low power, because for this Intel processor with the dissipation power at 65 watts, is now only consuming 9 watts of power in total, because we are only running at 1.2 gigahertz for all processors at this time. And the total amount of energy that we spend is 165 in executing this job. And now, Let me restore the frequency again. Okay, so that now we are at the frequency of 4.6. That was the default frequency of this processor. And now let's run the send job again and see what we get. Okay, as you can imagine, it only takes about 4.7 seconds to execute it. The power consumption is now 40 watt. The energy consumption is 191. So it's indeed more than what we used to have. So for this case, you will see a few things. So first of all, the power consumption indeed increased. However, the energy consumption did not increase as linearly as power consumption. So here we got 4 times more power than the previous one. However, the energy consumption only slightly increased by around like 25 joules, right? So well, it's not completely related, right? And is there a case that we are going to see a chance that the power consumption is not related to your energy consumption? So now I'm going to show you another program, which is the pop count, which we are also familiar with. So now if I am running the pop count with full power, as you can see, the power consumption is 34 watts and the energy consumption is 79. And now if I change the frequency again, lower the maximum frequency, and let me run this program again. Okay, so now if you run this program again, your energy consumption is about 77 and power consumption is 9 watts. So it's almost identical, right? So here you can see that, well, there and now if I try to have some more runs, maybe it will be different, right? So now if I run again, then it's 78 versus 77, right? So you see that there's not really a case that there's not really the case that your frequency would be completely or say your power consumption will be completely related to your energy consumption. And there are cases that you will see that if we lower the power consumption too much, and it turns out that your execution time increase a lot, then your energy consumption would be a lot more than the past, right? So remember this, right? Power consumption is just a moment, but the energy is also related to execution time. So if you lower your power consumption too much, then your energy consumption, if you lower your energy power consumption a lot, but it also increases your execution time a lot, then there is a chance that your energy consumption is going to increase a lot, because energy consumption is related to power consumption, and decreasing this will necessarily increase the execution time. And if the ratio of the decreasing and the increasing doesn't really compensate, then your energy consumption will eventually goes up, because you are going to take more time to execute your job. So that's why lower power does not necessarily means better battery life, because it takes you more time to finish the task that you want to execute, right? So that's what the demo is trying to tell us. And however, power consumption does have a direct meaning to in a lot in the heating this heat dissipation cost. So you see that right now, instead of giving you a processor with very, very high clock rate, we are seeing more multi-core processor. So assume that, so for this question, we assume that if we have an application that can be fully parallelized by 60%, right? And or it can speed up linearly with the clock rate. Should we double the clock rate or double a core, right? Duplicate a core. So the red one, we are doing the math on duplicate a core. So saying that if you have 60% parallelizable, and given that you know m loss low, you can assume that there is a 1.43 times speed up. And if you try to duplicate the core, you are just increasing the number of transistors on your chip. So it turns out that your power consumption is 2 times more. And the energy consumption, if you do the math, you will figure out that, well, it looks like this. And because you speed up 1.4 times and your power consumption goes up by 2, so it will consume 1.4 times more energy. However, if you double your clock rate, then turns out that your power consumption would goes up by 8 times, and your energy consumption will be 4 times more in this case. So that's why you are seeing, and because the power consumption goes up by 8 times, there is no chance that we can dissipate the heat generated by the chip appropriately. So that's why you are seeing that now we are pursuing more and more on the root of multi-core processors instead of a single core processor running at a very high frequency. So, and now if you look at the processor you have, the processor speed is dynamically switching between a range. So, and that's also because we want to reduce the power consumption when we are operating on the chip to make sure that the chip always operate in the allowed heat dissipation cost. And well, and this is usually done by the processor providing an interface to the operating system, and the operating system, as you can see, it's written by the programmer, so the programmer can control, right? So if I am an Apple programmer, right, I can definitely use that feature to say, hey, I detected you have an iPhone 6, then I'm going to lower your processor frequency. In some sense, I'm telling you that I'm saving more battery for you. But in another sense is that you are going to slow down your iPhone performance, and people will feel like, oh, it must be my iPhone is old, so I have to get a new one, something like that, right? So here you should have a strong feeling about like, okay, how the power consumption would affect your battery life and your application performance. But if it turns out that you have to use an app for more time, you have to turn on your monitor, your screen for more time, it's not definitely always the case that you are going to have a longer battery life. So that's a miss between the power and energy. So going through that demo, first of all, right, I guess all of you would agree with 1, 2, and 4. However, the third one, lowering the power consumption doesn't necessarily help extending the battery life. As you can see from our demos for the pop count programs, the power consumption doesn't really decrease. The energy consumption doesn't decrease as we lower the power consumption. So the answer is actually D for this question. Only 3 of them are correct. So instincts, you guys are correct, although you didn't give me the expected answer, but at least you guys are skeptical about the third one, right? So that's a good thing. Now, given now you know the concept of power consumption, I want you to think through this question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's look at what you guys think. So, wow, it's like a letter. So more of you thinking about like it's D now, but it's definitely a good chance because sometimes the 3 that you are thinking, it may not be the 3 that other people are thinking. So let's have a group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, aha, now I see more of you think it's E. So, the discussion does help a little bit. So why don't we just pick a team to share your thoughts with us? Okay, Valor. Who is the scriber of the day? Why do you think the answer is that? Okay, Daniel.
Hi, can you hear me?
Yes.
Okay, so our group thought that it was E because if you're cramming more transistors into the same chip area and the transistor power consumption remains the same, obviously the power consumption of the chip will increase, and so will the power density. So 1 and 2 are already correct. And then for 3 and 4, I think they mentioned some of this in the dark silicon paper. And for 3 specifically, they can't, or they mentioned that you can't turn on all of the chip at high frequencies because of thermal dissipation or heat dissipation limits. And then, so we think that 3 is also correct. And then for 4, with the same power budget, if we decrease the frequency using, I think they neglected to mention DVFS, or neglected to consider DVFS in there. But if we lowered the clock rate of all of it to something that to a level that basically lets the static power overwhelm or basically, what am I trying to say here? Basically, what I'm trying to say is that the dynamic power from keeping the CPU frequency low doesn't push the thermal threshold, or doesn't push the power consumption beyond the thermal threshold with the static power. And the static power is obviously going to go up because of the number of transistors in the chip. So we also think that I'm a little suspect of 4, but it's I would still consider it correct.
All right. So if you look at that, right? So basically, we are saying is, if you remember the picture that I draw in the past, right? So if you have a chip that you can reduce the power consumption per transistor to be half. So for example, like Daniel, you just said, if we can use DVFS to reduce the power consumption to be like this, then we are still fine, right? But if it turns out that we have a chip like this, right, which the power consumption per transistor is really high, then turns out that if you want to power on the whole chip, then it takes twice of the power, meaning that the density of the power is really high, or the total amount of power that you need to turn on the chip is really high. Right, so if you want to maintain the same power budget, you can only leave half of them on, half of them dark. That's called dark silicon, or you have to find a way to make this happen, right? So and if you want to find a way to make that happen, then dynamic voltage scaling is definitely one of the ways you can use to achieve that goal, right? So that's why I would say all of the statements here. Why it's jumping around like this? So you will see that all of the statements here, they are all considered as correct. And that's the reason. So, and I'm glad that after the discussion, all of you discovered that. So now, as Daniel, as Tim Valor just mentioned, that we should talk about the dark silicon provenance. Dark silicon is the paper that give you insights on this. So let's look at what the paper is saying about. So dark silicon paper is talking about, in addition to leakage power, in addition to dynamic power, when we are entering the era of advanced technology, like advanced process technology, the leakage power is being more and more significant. So like what we have in this figure, right? In the past, dynamic power is really the majority of the power consumption. And now the leakage power is probably around half of your power consumption. And as we said, if we could adjust the voltage, we can shrink the amount of dynamic power, but not to the leakage power. So yes, for statement 4 is very suspicious if the leakage power goes up to something like this. However, because right now we are still in an era that dynamic power still have at least like 33% of the power consumption, so it does help a little bit in making sure that our chip is still within the power budget. And usually when we design the chip, we have sufficient amount of margin in the heat dissipation cost. So 4 is still a true statement for now, but may not be forever, right? So but for leakage power is really the dominant factor for most of the advanced technology process technology right now. And the leakage power, the power consumption is like this. And I don't know too much about this, but it's the supply voltage and the threshold voltage, which are considered as some kind of constant values in a chip design. And the N is the number of transistors. So you can see the leakage power is indeed related to the number of transistors we have. And what is leakage power? It's just because we are not living in a perfect world. And those transistors, they may leak electrons when they are operating. So that's why we are having leakage power when we have the chip. So in the past, the leakage power is scaling well with your process technology. However, right now, because of the process technology, I don't know why, but that's not my area. Although right now I'm teaching in ECE department, but I'm actually having a CS degree, so I'm not really knowing a lot of this like details about the electron stuff. But right now, at least what you should know is about like these three boxes, right? When we have leakage power, when we have the in the current process technology, classically we are able to scale the supply voltage and the threshold voltage of a chip by the scaling factor of your process technology. But right now they don't get scale, and as a result, your saturation current also doesn't get to scale. So turns out that the power per transistor remains the same, and if you are going to put more transistors inside, the power consumption per chip is also going to be S squared, and the utilization, meaning that the amount of power that you can distribute to a single transistor is like this. So turns out that we are seeing a dark silicon problem now, right? So that's why we have this dark silicon paper that assigned to you, and it gives you a good idea about like, okay, right now we are in the era of dark silicon. So you are seeing that because of that, the clock rate of modern processors are limited, because even though I have more advanced technologies, the supply voltage that's related to my frequency, right? It's not changing. So my frequency cannot increase anymore. So you are seeing that very slow improvement in the frequency right now. And since 2003 and 2018, the clock frequency of processor is staying is only about like 2% improvement per year. But in the past, we can achieve like 40% per year. So we are indeed in a dark silicon era right now. So in the following lectures, I'm going to talk about what are the solutions and trends we are seeing in dark silicon era. So here are 4 things that I conclude. So first of all, right now you are seeing more and more chips with aggressive dynamic voltage and frequency scaling. And the architecture design is going to be more throughput oriented, meaning that we are going to have a lot of slower logic, but we are going to give you more to give you the throughput that you need. And the third design strategy that I've been seeing is that because it's dark silicon, we just create a lot of stuff that doesn't need to be power on during the normal cases, but we just turn it on actively, proactively whenever we need it, but turn it off whenever we don't need it. And it also means that it also gives you the chance of seeing that in the past, we tried to design something that's going to be more general purpose, but now you are seeing more and more domain specific integrated circuits like called ASICs, application specific ICs in modern computers. So these are the trends we are seeing in dark silicon era. And now the first I'm going to talk about is the very aggressive dynamic frequency scaling. So if you look at the modern processors frequency, like this is the data sheet that I just pulled out from an Intel i9 processor yesterday. You can see the processor has a base frequency of 3.6. mix. And as I demoed a lot before, that if you have the frequency scaling set up correctly, most of the time the processor, when it's idling, is just operating at something like 800 megahertz instead of the full power. But actually, if in some cases, right, if they could potentially turn off or say lower the clock frequency of all other cores and just letting single one core goes up to 5 gigahertz. So that's what they call turbo boost in the Intel processor technology, meaning that we slow down all other processors, allowing one processor that's busy working on a single thread at its maximum frequency. So that's the technology. One of the things that you are seeing, that all processors right now, they have very aggressive dynamic voltage frequency scaling to solve the issue. And as you can, as we learned before, the voltage and frequency scaling is helping the dynamic power per transistor, but not the static power per transistor. But as I just mentioned, right, because the dynamic power is still a significant amount of power consumption, so it does help you to guarantee that at least your chip can fit in the power budget that we have. So, and that demo, I think I have to show you, right? And static leakage power. So, so very aggressive dynamic voltage frequency scaling help us to address the dynamic power issues. But how about the static power? So it turns out that we have the second trend. We are seeing slower but more functional units. So this is another comparison of a few Intel's server processors. And as you can see, we just compare these two processors. So the E7-8890 and the E7-8893, both of them are at the same core technology. However, if you look at the base frequency of these processors, if you have 24 cores, it turns out that the processor frequency is going to be slower, as I just mentioned, right? We want to lower the dynamic power, right? So turns out that that's also a case that we are seeing slower but more in the dark silicon era. And another paper that's about this is this. Single instruction set architecture, heterogeneous multi-core architecture that you've probably already read. So one of the author, Noam Jopi, you already know him. He is also the author who wrote a paper of prefetch buffer. And also Ding Townsend, he is also the my advisor, also the who invented simultaneous multi-threading, right? So for this paper, what it talks about is that, okay, so those chips with more advanced technologies, they tend to be more power consuming when they are operating, because they either have higher frequency or they need more power to perform the same task. So within the same area, we can actually try to build, we can shrink more small cores, which each of them would be slower, but you are going to have more. So in this way, you can imagine the consequences is that you are going to have very good thread level parallelism. So for example, given the same chip area, you can either build a 20-core processor or a 3-core processor with high-end core, an 8-core processor with high-end cores, and 5 cores with slower cores. So that's the idea of single instruction set architecture heterogeneous chip multiprocessor. So since you already read the paper, now I want to invite you to look over the statements and tell me what you have learned about this paper and how many of them do you consider them are correct. Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what you guys think, it looks like C is the most popular answer. However, B and D, they are also popular. So it's definitely a case that we should go to group discussion. Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like, well, B is getting more popular now. But in the meantime, we also see a lot of you think the answer is C still. So we definitely, it's a good case that we should find a group to share your thoughts with us. So let me see. Well, how come it's always Valor? Okay, it looks like you are really giving a chance. You are really having a chance right now. Valors, what do you guys think? Okay, Daniel.
Hi. So we thought there were two things correct, sort of by process of elimination, either two or one. But for the first one, you don't need to recompile and optimize the binary for each core
Why?
architecture. I don't remember. They mentioned it in the paper. I think it was also
yeah, but what's the
quiz
keyword
question.
here why you don't have to recompile it?
Because the ISA is the same.
Right, it's single instruction set architecture, right? So even though there are different generations of cores, but it's just different generations, so you don't have to recompile.
Okay, so that one is wrong. And then for number 4, spending more instructions on older gen cores would lead to better energy delay. I didn't think that that was true, or our group didn't think that was true either.
But do you have the evidence? It's actually from the paper, right? If you look at the graph, right? So like this one, you spend more instructions here, but turns out that the amount of instructions is, if you look at this one, it spent only 54% of instructions in EV6, but the energy saving is, and the energy delay is better, right? So that's an evidence. What else?
And then I didn't have the paper in front of me, but I think there was something that was mentioned for number 2 being correct. For a program with limited thread level parallelism, single ISA CMP would deliver better or at least the same level of performance. And they had, I don't have the paper in front of me, so I can't quote it, but I think that.
So why? So if you have limited thread level parallelism, meaning that you are going to use a few cores, right? Very few cores, right? So single instruction heterogeneous chip multiprocessor has one of the most advanced cores in hands, right? So and if the amount of advanced cores you have is sufficient enough to cover that thread level parallelism, you are going to deliver equivalent performance as this one, right?
Yeah.
Okay. So
similarly, we thought the same reason for option 3.
Okay.
Yeah.
Okay, great. Okay, so looks like right now Valors and Mystic, you guys have a tie. So next lecture will probably be the two teams have to have have to compete with each other. But before we finish the lecture today, there are quite a few things that I have to mention. So that's why I have to finish the discussion, and we are going to resume the discussion on single instruction set architecture chip multi-core processor. So the last lecture is this Wednesday. We will take a group photo together. So prepare your virtual background, shave your birds or whatever, right? Probably a while you haven't seen other people. Project due tonight, no extension. And I sent an email last night because I got complaint from the admin. I don't think I have to say more about that. We have the last assignment due this Wednesday. I eval until December 11th. And in 10 minutes later, we are going to have a talk by Ritu Das today and attend and submit a screenshot counted as a full credit reading quiz. So the last chance you can boost up your reading quiz grades. And one more thing. Right. One more thing that a lot of you care about here is the comprehensive guidance about the final exam. And I just figure out that the island has some limitations, so it won't show this when your exam starts. So these are a few things. The final exam can only be open once, and it covers everything. And this is an open book, open note. But again, you have to make sure that your computer won't have issues. And we have many questions for you. And please show your work if appropriate. And there's no partial credits for multiple choice questions. Please think thoroughly and reference online solution. And late submission is not allowed. And we will release a sample final at the end of the last lecture. A lot of you were asking about CEP, the comprehensive exam. So we have 2 problem sets are considered as comprehensive exam. One problem set is Q21 to 25, and the other is 26 to 28. You have to get 60% from each to consider as a pass. Other than that, I will see you in the talk. I will see you in the lecture. I maybe see you in the office hour.